Good afternoon, good morning, good evening, wherever you are. Welcome to another edition of the seminar series of the Microsystems Technology Laboratories. I am Jesus Del Alamo, Professor of Electrical Engineering at MIT. Today we have the privilege of hosting Sean Lee, who is the co-founder and the chief hardware architect at Cerebras Systems. He holds bachelor's and MEng in Electrical Engineering and Computer Science from MIT. And after graduation, he went to AMD and eventually became the founder and lead architect of C-Micro, a company that was acquired by AMD. So he went back to AMD, where he became a fellow and the chief data center architect. And eventually he moved on to found Cerebras, which is the work that he's going to tell us today about. Cerebras, as you will see, has built the world's first and only wafer scale AI processor. And this is really an extraordinary chip, if you could call it that way, and you will see why I say that. And that's the topic of today's show. So Sean, thank you very much for joining us today. We're very much looking forward to your presentation.
Thank you, Jesus. As Jesus said, I'm Sean. I'm the co-founder and chief hardware architect at Cerebras Systems. And when we started Cerebras, we had a vision to drastically change the landscape of compute for AI. And in today's talk, I'm going to share with you some of the outside of the box thinking that we believe is necessary to meet the demands of ML in the future. So for those of you who don't know about us, Cerebras started in 2016, really just at the beginning of the modern deep learning era. And our mission was to solve the problem of AI compute by building a full AI accelerator solution. That's from the chip to the system to all of the software. And now we have engineers and customers all around the world. And really what an incredible journey the last few years have been, both for us as a company, but as I'm sure you can agree, for the entire ML industry. But I'm here today because we believe we're really just at the beginning of what neural networks can do. And we're already reaching a pace where traditional approaches just can't keep up. In 2018, state-of-the-art neural networks had 100 million parameters, and that was already a lot. But in 2019, models like GPT-2 and Megatron, they were 10 to 100 times larger. And then in 2020, we got GPT-3 with 175 billion parameters. And in fact, just a few months ago, Microsoft announced their MTL model with a staggering 530 billion parameters. And there's no end in sight. Tomorrow, the industry is going to want to run models with trillions of parameters. So when you step back, you can see that that was 1,800 times more compute in just 2 years. Let me say that again, that's 1,800 times more compute in just 2 years. And as a computer architect, and really for all of us in this community, this is both an exciting and daunting problem at the same time. So let's take a look at how we as an industry have responded to this unprecedented demand from these new ML workloads. The exciting part is that we as an industry have been hard at work and we've seen some remarkable innovations. In fact, those models that I just showed you, they wouldn't have been possible without some of these. And here are a few examples. In just the last few years, we've been continuing to improve process technology from 16 nanometer to 12 nanometer, and now 7 nanometer chips are used daily. We've also seen advanced packaging technologies to enable higher bandwidth memories, for example. We have lower precision numerics, such as floating point 16 or bfloat 16. And we have new data path designs, such as systolic arrays or tensor cores that can improve compute density and power efficiency. So let's take a deeper look at these improvements. First, let's look at process. And on the right, I've plotted the transistor density of GPUs over the past 10 years or so. And as you can see, the process industry has been continuing to improve at an incredible pace, and in large part because of what this community here has been doing. So Moore's law is not dead. And in fact, we see this trend continuing for the next few years. That's very exciting. Next, let's look at the other innovations. And here, broadly speaking, I'm going to group all of these into a category I'm calling architecture and microarchitecture. And on the right, I've plotted the metric peak flops per transistor. Again, for GPUs, also over the last 10 years or so. And here I'm using this metric flops per transistor as a rough measure of architecture performance. And what's really impressive is, as you can see, there's a very healthy increase and clear trend over time. In fact, it's keeping up or even outpacing Moore's law by a little bit. And for me as a computer architect and for the architecture community, this is really exciting to see because architecture matters. Now that's the exciting part. If you look at the last 2 years, we got about a 2 times improvement from process technology, Moore's law, and we got about a 3 times improvement from architecture performance. But now comes the daunting part. In that same 2 years from BERT to GPT-3 on the neural network side, as we just saw, the ML demand increased 1,800 times. Now that's a 300 times gap. And how did we as an industry meet that need? Well, it all came from system scale out. In fact, when OpenAI trained GPT-3, they used 1,000 GPUs. So when you step back, the performance gains over the last couple of years in the industry have been completely dominated by system scale out. So the answer is just scale out, right? The ML demand certainly doesn't appear to be slowing down. So you might think that we can just rinse and repeat what we've done in the last 2 years and we can satisfy the needs in the next 2 years, right? Well, let's imagine what that might look like. Say we get another 2 times improvement from Moore's law. We do have 5 nanometer and 3 nanometer in the pipeline. And let's say we get another 3 times improvement from architecture, maybe higher density compute data paths, maybe even smaller numeric formats. And then lastly, another 300 times from system scale out. Is that possible? That would mean clusters on the order of 100,000 chips. And while not technically impossible, I think we can all agree that's not very practical. In fact, just the sheer cost, power, and physical footprint would be prohibitive. And perhaps most importantly, it turns out that these existing scale-out techniques, they're not actually easy to deploy, and they're actually not that scalable. And the reason is that fundamentally, these giant neural network models, they need massive memory, compute, and massive communication to tie them together. And when you try to provide all of this using thousands of small devices, it turns the scaling of all 3 of these into distributed problems that are interdependent. It really becomes an explosion of this distribution complexity to get them all to work together to solve a single large problem. And this complexity grows dramatically as the cluster size grows and becomes quite overwhelming at large model sizes. So instead, for all of these reasons, with the existing scale-out techniques, we think there may be up to another 10 times improvement on scale-out, but probably not much more than that practically. So that would give us cluster sizes on the order of 10,000 chips, maybe. In fact, we're starting to see some evidence of that. When GPT-3 was trained in 2020, it was on 1,000 GPUs. And a few months ago, when Microsoft announced their MTL model, that was trained on 4,000 GPUs. But we believe this scale-out trend is not going to continue much further with existing techniques. So where does that leave us? With the current approaches, the industry possibly has a path to another 60 times improvement over the next 2 years. But we need 1,800 times. And that is the grand ML demand challenge in front of all of us. We must find ways to substantially improve across the board, to improve process beyond Moore's law, to improve architecture by orders of magnitude, and to improve and simplify scale-out substantially. All of this is going to be required for us to have any hope of keeping up with the ML demand. So let's imagine what a world would look like with more balanced scaling, where we get another 10 to 50 times improvement on process and architecture and truly scalable clustering. Is that even possible? Well, we believe it is. but only if you think about the problem differently, by thinking outside of the traditional box with true end-to-end co-design. We believe this is possible. And in this talk, I'm going to highlight some of the possibilities when you truly embrace this extreme co-design approach. Let's start with process. As we just saw, Moore's law is not dead, but can we amplify it even further? Historically, transistor density improvements have been amplified further by gradual increases in die size. And on the right, there's a plot showing die size over the last several decades or so. And as you can see, there's a steady increase. But unfortunately, we're hitting a wall now, and die sizes are not getting much larger. And there are a few primary reasons for this. First, larger chips have very low yield. Second, there are fundamental challenges in lithography that prevent increasing the reticle size. Third, significantly larger chips have significantly larger problems in handling thermal expansion. And then lastly, larger chips are more difficult to power and to cool. Now, the industry has been creative in finding ways to extend beyond the single die and solving some of these problems. For example, with advanced chiplets and MCM techniques, we're seeing maybe 2 to 5 times more silicon area in a single device. And recently, we've been really encouraged by early announcements of concepts using advanced interposer techniques, even using entire wafers as interposers. And these techniques, when they're available, might achieve up to 20 times more silicon area in a single device. And we believe that techniques like this are highly valuable because they extend the effective size of the chip. But let me show you what we've done at Cerebras to show it's possible to push even further with tighter co-design. In 2019, we introduced the wafer scale engine. And last year, we announced the second generation. It's the largest chip ever built. It's 56 times larger than the largest GPU today. And it's a single piece of silicon. It's in fact the largest square you can carve out of a round 300 millimeter wafer. That's 215 millimeters by 215 millimeters square, or about 8.5 inches per side. In that size, it's over 46,000 square millimeters. We can fit 2.6 trillion transistors on a single chip. That's 850,000 compute cores. And with all of those cores integrated on a single piece of silicon, we can get some truly mind-boggling numbers for memory and fabric bandwidth. Because everything is on chip. Now, to do this required some deep co-design to solve the 4 main problems of yield, process, thermal expansion, and power. Yield is a problem even for traditional small chips, so it becomes fundamental for extremely large chips. In fact, at the wafer scale, it would be literally impossible to yield a full wafer with no defects, because defects in silicon and in manufacturing, they're just a fact of life. They can't be avoided, even in mature processes. So to solve the yield problem, we use redundancy. Here, we architected our chip as a giant array of uniform small cores connected with a 2D mesh fabric. And the design includes redundant cores and redundant fabric links. The picture shows an example. There are extra redundant cores built into the hardware shown on the top. And on the left, when there's no defects, the redundant cores, they're not used. But on the right, when there is a defect, we use a redundant core to take its place, and then we reconnect the fabric using the redundant fabric links. And this fully restores the logical fabric. And with this technique, we can drive yield very high with very low additional cost. But this is only possible because of co-design with the chip architecture. In fact, as you can see, the yield solution, it's baked directly into the fundamentals of the fabric design itself. The second major challenge is how do you extend beyond traditional lithography limits? Now, creating larger reticles has fundamental challenges. So instead, we work within the standard independent die on a single large wafer. But instead of cutting up these individual die into individual chips, we cut out the largest square from that wafer. In the standard fab process, these independent die are separated by scribe lines, which are used as mechanical barriers and for test structures. But we add small wires to cross these scribe lines to connect these otherwise independent die. And we do this using high metal layers in the process. And this extends the 2D mesh fabric, resulting in a fully homogeneous array of cores across the entire wafer. Now, again, this is only possible with tight co-design between the fab, in our case, TSMC, where we've developed a technique in partnership with them, where we essentially fill these scribe lines with tens of thousands of small wires. And that required changes to the fab process since these scribe lines contain TSMC test structures. Now, these seemingly short, small wires, they're a really big deal because they provide the same bandwidth within a die, but across the entire wafer. And that's only possible because we're spanning less than a millimeter of distance on silicon. And for chip designers, we do this all the time without even thinking about it. The tools just take care of it. But when you compare that to traditional approaches, which are usually SerDes based, this difference is massive. And the reason is really just physics in some sense, because driving bits less than a millimeter of distance on chip, on silicon, is much easier than through a package, through connectors, through circuit boards, and sometimes even cables. And this results in orders of magnitude improvement compared to traditional I/O, as you can see in the table. We're able to achieve about an order of magnitude more bandwidth per unit area and almost 2 orders of magnitude better power efficiency per bit. But there is really a clear trade-off here. And in many ways, by moving the communication problem onto the chip, we've made it much easier. But we shifted that complexity that would have otherwise been in the chip in the form of the SerDes circuits, and we shifted it into the package. So this is really only possible with extremely tight co-design with the package and the system around it. So let's look at the package. One of the main challenges here is thermal expansion. And as you can see in the cross-section picture on the right, we have silicon on the top and we have a PCB on the bottom. And no surprise, they're made of different materials, so they expand at vastly different rates. The CTE of silicon and copper, they're vastly different. But this is a big deal because of the size of the wafer means that that variation across the chip is much larger. So large, in fact, that it would result in too much mechanical stress if we use traditional packaging technologies. Remember, the chip edge is 215 millimeters per side. And with the high temperature changes that are typical in processor chips, that mechanical variation can be quite high. So to solve this problem, we developed a custom connector to connect the wafer to the PCB. And this connector has special properties that can absorb the dimensional variation while maintaining connectivity. And as you can see in the picture, the largest variation occurs at the edges where the connector has to absorb the most variation. Now, once you've solved the thermal expansion problem, we need to turn our attention to the power problem that generated that heat in the first place. And here at the package level, what we've done is we've taken all of the silicon that would have been traditionally spread out physically across the PCB, across maybe even different servers or different racks, and we've concentrated all of it into a single location, consuming on the order of 20 kilowatts of power. And that concentrated high density exceeds traditional power and cooling capabilities. On the power front, we need to bring the power in. And traditional current distribution is done through power planes laterally in the printed circuit board. But the current density here is just simply too high to distribute laterally through the PCB. If we did that, we'd really only be powering the edges of the wafer. And on the cooling side, traditional cooling is done through direct airflow. But again, here the heat density is just simply too high for that to be effective. If we did that, we'd only be cooling the edges of the wafer. So here, our solution is to co-design a 3D package. We can bring the current in perpendicular to the wafer by going directly through the PCB. Remember, we have on the order of 44,000 amps of current. And so this can be done only through direct perpendicular access to the wafer. And then we bring the heat out also perpendicular to the wafer by using water flow through a cold plate on top of the wafer. That current ultimately translates into over 20 kilowatts of power in the form of heat. And this solution allows us to power and to cool every die evenly, both at the edges and the middle of the wafer. But as you can already see, this isn't your typical chip package. So it needs to be co-designed with the full system around it. And this is what that system looks like. We start with a wafer that's held vertically. And then it's surrounded by what we call the engine block. This is really the subsystem that holds the wafer and the package. We bring the power in from the front, again, perpendicular to the wafer, and then we take the heat out from the back. So now let's take a deeper look at what's inside this engine block. We start with the wafer that's held vertically. And in front of the wafer is a block of voltage regulators bringing power in. And as you can see, this is a very dense block, which also needs to be cooled using a similar approach as we cool the wafer. And that's done with a cold plate on the back where we run water through so that we can remove the heat from the wafer. That same water is also circulating into the regulators. And the water that's being pumped through here is then directed through a manifold that's connected to our pumps. And then lastly, we take this engine block and we build the entire system surrounding it. And here, the entire system architecture is co-designed to support that wafer scale chip from ground up. At the system level, we have power supplies in the front, right next to the water pumps. And then there's a heat exchanger below to remove the heat externally. At the system level, again, power comes in from the front, all perpendicular to the wafer. The wafer generates the heat, and then the heat is then removed from the back through the water being pumped through the cold plate, and then down into that heat exchanger below to be removed from the system. And then lastly, that cool water is recirculated back to the wafer, forming a fully contained internal water loop. And this is what the system looks like. This is a system where every detail is co-designed to enable a chip that's 56 times larger than traditional chips. With this level of co-design between the system, the package, the fab, and the chip architecture, we can literally push the envelope of die size well beyond traditional scaling. And new co-design approaches such as wafer scale chips and other novel techniques, we believe are a critical part to solving this grand challenge in front of us, because it enables us to push the process gains by as much as 2 orders of magnitude and achieve cluster scale performance on a single chip. But that's only one component of solving this grand challenge. Next, let's look at architecture performance. Imagine what's achievable if we designed an architecture from ground up for neural networks. Neural networks are generally expressed as a series of gem or matrix multiply operations. And this is a really valuable and simple way of expressing this computation. And as a result, architectures have evolved to run dense gem matrix multiplies at higher and higher densities. This is in fact one of the primary sources of architecture improvement in our industry. It's a big part of that 3 times speed up we've seen in the last couple of years. But can we continue this approach and get another order of magnitude or more speed up? Unfortunately, I think that's unlikely. And the reason is because the physical and power considerations means you can fit only so many fmax circuits onto a chip. And as you build larger and larger matrix multiply data paths, the larger the penalty is if the workload doesn't fit exactly. In fact, as these data paths increase in size, the utilization can actually drop. To get significant gains, we think we need to change the rules. And so we asked ourselves, what if we could get the same results, but with fewer flops? Is that possible? It actually is. And that's because neural networks are naturally sparse. And in fact, thinking of them as just dense gem matrix multiplies is missing some fundamental properties of neural networks. Sparsity arises when there are zeros in the computation. And the main operation in neural networks is a multiply-add operation. And as we all know, multiply and adding by 0 doesn't change the result at all. Sparsity can arise in neural networks for a variety of reasons. Sometimes it's from common ML techniques like ReLU or dropout, and sometimes there's sparsity when you might not even expect it. For example, there are nonlinears that introduce sparsity in the backward pass of training when the forward pass is actually dense. And in addition, even dense neural networks, fully dense neural networks, they can be made sparse. In fact, inducing sparsity is often already done in inference today. And it's not really surprising because from an intuitive sense, neural networks are by definition over-parameterized. And the act of training, in a sense, is really just trying to discover which of these parameters are important and which are not. And the machine learning community is inventing techniques to exploit this property every day. I've listed a few examples here of sparsity algorithms from the ML research community, and they're showing up to 10 times flop reduction and sometimes potentially even more. So imagine the architecture that could harness this potential and enable the ML community to innovate on yet newer and sparser models. That would be a level of ML and hardware co-design that simply isn't possible with existing matrix multiply approaches. And that's because these traditional architectures are fundamentally at odds with the fine-grained, unstructured, dynamic nature of sparsity. That's because these hardware data paths are physically hardwired to perform structured matrix multiplication. And this structure works actually very well when you're doing a dense matrix multiply because it enables a very compact and efficient design. But this structure is ultimately a fundamental limitation when there's sparsity because there's less data reuse and there's less overall structure in the computation. But what if we could design an architecture with sparsity as a first-class citizen? And we can solve this fundamental constraint and open up the vast opportunity for ML and hardware co-design. There's really a large spectrum of ways to handle sparsity at different granularities. But let me show you how we've addressed this at Cerebras to demonstrate that it's possible to accelerate even the most fine-grained dynamic sparsity. Here, we used fine-grained data flow scheduling. That's where all of the compute is triggered by the data. In the Cerebras compute core, the fabric transports data and all of the associated control, all of it in hardware. Once the core receives the data, it triggers the tensor instruction to run. And with this data flow mechanism in the cores, the entire compute fabric we think of it as a data flow engine. And this is what enables native harvesting of sparsity, because we can simply filter out all of the zero data at the sender. If the sender of the data doesn't send any information, and since all compute is triggered by the data, the receiver doesn't perform any compute. It's really that simple. So not only do we save the power because we're not performing all these wasted operations, but we also get acceleration by skipping all of that wasted work and using those cycles to perform the next useful work. Now this, again, is only possible with tight co-design, with the machine learning and the compiler and the kernel software. On the machine learning side, this natively accelerates natural sparsity, but also enables that co-design of new sparse ML models. And on the software side, we co-design our software to be data flow aware from ground up. Let me show you what that looks like. To illustrate, let's look at a sparse matrix multiply kernel as an example. We consider our entire wafer as a single giant sparse matrix multiply array. Here's how that works. We start with activations distributed across the wafer's on-chip memory, and then we stream weights through. As these weights stream through, they trigger the multiplication with the local activations, one individual weight at a time. This is where we're using that fine-grained data flow mechanism that's built into the hardware, performing a single vector scalar multiply for every weight as it streams through. And we skip all the zero weights. The full memory bandwidth is what's enabling all of this at full performance, and then the resulting partial sums are accumulated using the high bandwidth fabric across the entire wafer. There's no need to block or partition the matrix because the size of the wafer is so large that we can operate on the full range of matrix sizes. And then lastly, we use the exact same flow for both dense and sparse computation. And here are some of the results that we've measured. In our lab, we've measured speed up for fully unstructured weight sparsity on GPT-3 size layers, all the way up to 90% sparsity. That's 10 times more zeros than non-zeros. And on the right, as you can see in our lab results, we're seeing near linear speedups even at this extreme level of sparsity. In fact, the only limitation here is really just Amtel's law because we have to amortize the fixed overheads. But our massive memory and interconnect bandwidth enables us to reduce that overhead pretty significantly. And in fact, that overhead reduces even further as the model size grows. These results demonstrate that we can accelerate fully unstructured sparsity, which is not possible in traditional matrix multiply architectures. And therefore accelerate all types of ML sparsity algorithms that are already available today, but also enable a new class of smarter, sparser models that are actively being developed. As a broader community, we believe it's through this level of ML co-design that we can practically reach these extreme scale models. And we can break free from traditional brute force flop scaling. In fact, we believe that these sparsity opportunities only increase as the model size grows. So coming back to the grand challenge in front of us, with techniques like sparsity enabling deep ML co-design, along with traditional architecture improvements, there is a path to driving an order of magnitude or more architecture performance. By changing the rules, we can go beyond just flops. And we can enable an entirely new class of sparse ML techniques co-designed with the ML community that are not possible otherwise. All right, we've addressed now 2 out of the 3 major components to scaling performance. So let's talk about the last performance, cluster scale out. Now, clustering solutions already exist today. As we saw, that's how We've trained these massive models. But why is it still so hard to scale? To understand why, let's look at existing scale-out techniques. The most common is what's called data parallel. Here, you take the model and you replicate it in every single device. And then the training data is split across the devices. This is the simplest approach because you're just replicating the model. But it doesn't work well for large models because the entire model needs to fit in every single device. Now, to solve this, the common approach is to run model parallel, where you split the model and you run different layers on different devices as a pipeline. This enables larger models because you can use more memory in more devices, but has significant communication overhead. And as you spread those models across more devices, the activation memory increases quadratically because you need to keep all the activations in the pipeline. So to avoid that, it's also common to run another form of model parallelism by splitting the layers across devices. But this also has communication overhead, and splitting these layers can get very complicated. So because of all of these constraints, today, there isn't a single one-size-fits-all way of scaling out to multiple devices. In fact, in most cases, training these massive neural network models requires a hybrid approach with both data parallel and model parallel. That's actually how OpenAI trained GPT-3, for example. So although scale-out solutions do technically exist, they're so complicated and limited that they're often not accessible to the ML community. When you step back, the fundamental reason for this is actually very simple. It's because in traditional scale-out, memory and compute are tied to each other. And trying to run a single model on thousands of devices turns the scaling of both memory and compute into distributed constraint problems that are interdependent. As the model size grows, we need to do more partitioning of the model onto more chips. We need to do more fine-grained coordination, more synchronization, and so on. If you've ever trained a neural network on a large cluster of GPUs, you'll know what I mean. In fact, large companies like Google and Microsoft, they have entire engineering teams just to figure out how to do this. But to solve this problem properly, we believe it's not about creating software solutions to hide all of that complexity, but instead by truly co-designing a solution at the cluster level and thinking outside of the traditional device. We believe it's possible to architect a solution that's inherently simple and scalable. Let me show you the approach that we're taking at Cerebras to demonstrate what's possible. It's possible to think of the entire cluster as the ML accelerator. And when you do that, you can architect the cluster level memory and the cluster level compute in a more natural and scalable way. At Cerebras, we're doing this in an execution model we call weight streaming. We first separate the memory from the compute, fundamentally disaggregating them. The reason we can do this is because neural networks use memory differently for different components of the model. So at the cluster level, we can design a purpose-built solution for each type of memory and each type of compute. And then as a result, we can untangle the two and completely simplify the scaling problem. Let's see what that looks like. We start with the primary compute unit, which is the Cerebras CS2 system, which has the wafer scale chip. Within that large chip, we have the large foundational building block that's large enough for all layers without partitioning. Next, to handle these models of extreme size, we add an external storage device to hold all of the model parameters, or the weights. We call this MemoryX. And it's designed specifically to scale up to extreme scale models capable of up to trillions of neural network weights. And then, completely independent of that memory, we introduce an interconnect to scale up the number of CS2 systems. We call this interconnect SwarmX. And it's also specifically designed to scale neural network training to cluster up to tens to hundreds of systems. In this execution mode, all of the model weights are stored centrally in that MemoryX unit. And then they're streamed onto the CS2 system as they're needed to compute each layer of the neural network, one layer at a time. The weights are not stored on the CS2, not even temporarily. As they stream through, the CS2 system performs computation using the data flow mechanisms I mentioned. And then the resulting activations, they stay resident on the CS2 system, ready for the next layer. During training on the backward pass, the gradients are streamed back in the reverse direction, back to the MemoryX unit, where they do the weight update. And so in some sense, you can think of this as a purpose-built memory hierarchy, but at the cluster level. And then, independent of that memory, we can scale compute. And this is done by simply clustering multiple systems with a specially designed interconnect for data parallel. This is what we call SwarmX. It sits between that MemoryX storage unit and the CS2 compute systems. But it's completely independent from both of them. The interconnect broadcasts weights to all the CS2s, and then it reduces gradients from all the CS2s. So in some sense, it's actually more than an interconnect. It's an active component in that training process, which is purpose-built for scale-out training. Internally, this SwarmX interconnect uses a tree topology to enable very modular and low overhead scaling. And because it's modular and it's disaggregated, you can scale to any number of CS2 systems with exactly the same execution model as a single system. Scaling to more compute is really as simple as adding more nodes to the interconnect and adding more CS2 systems. And lastly, since the underlying hardware architecture supports sparsity natively, this cluster also supports sparsity natively. Sparsity is induced in the weight matrix in the MemoryX unit, and then the sparse weights are streamed to all the CS2s. The SwarmX interconnect broadcasts them all in sparse form, and when the CS2 receives them, it performs the computation all in sparse form, again, using the underlying hardware data flow mechanisms. All of this is happening natively with no change to the weight streaming model. In fact, it's exactly the same flow as dense. So with this interconnect architecture, we project near linear performance scaling from a single CS2 system all the way to 192 systems. And here's how that scaling translates into training speedup. Here I've shown training speedup for a range of natural language models from 10 billion parameters all the way to a hypothetical 100 trillion parameters. This is using the scaling laws of NLP models published by OpenAI. And for reference, the largest language models today, like GPT-3, they're around a few 100 billion parameters. So as you can see, the scaling is actually near linear and mostly falling off for relatively smaller models where the batch size becomes a limitation beyond a certain point. But for relatively larger models, we expect the scaling to be near linear all the way to 192 systems. So, as you can see, by changing the rules, by thinking beyond the individual device and thinking holistically at the cluster level, it's possible to solve the fundamental challenges of scale out today. And it's possible to execute exactly the same on a single device as for hundreds of devices. And that's how it's possible to address the final component of the grand ML demand challenge in front of us. Scale out that's actually inherently scalable. So now let's go back to where we all got started today. In the past couple of years, we have seen over 1,000 times greater demand from the ML workload, and there's no end in sight. In the next couple of years, this is where we'll be. On first glance, this might seem daunting and not possible. But what we've seen today is that it is in fact possible, but not by using traditional techniques. Only if you change the rules. Only if you think outside of the traditional boundaries. We believe this future is achievable. Only with deep co-design, it's possible to do some truly remarkable things. It's possible to build chips beyond individual die. It's possible to push compute beyond brute force flops. And it's possible to design an architecture with inherently cluster scale performance. What an incredible, exciting time it is to be in this field right now. I've shared with you just some of the approaches that we're taking at Cerebras to pursue this future as an example of what's possible, and I'm so looking forward to what we and the community come up with next. Thank you very much.
John, thank you very much for a really extraordinary talk, and congratulations on truly extraordinary work. This is just so impressive. It's such a gigantic breakthrough. All right, we have a few minutes to take some questions from the audience. Use the chat or use the Q&A, and we will try to pass you the controls, or rather the mic, so you can ask the question yourself. I don't see anything at the moment, Q&A and the chat. So let me ask the first question, Sean, while folks warm up to asking their own questions. You mentioned at the beginning that the solution to the yield problem was to reconnecting these elemental cells, I forgot how you call them, bypassing those that have a defect and bringing alive those that have been dormant on the side, prepare for this. Is that reconnection done at the manufacturing level? You, in some point in the process before the wafer is finished, you check electrical activity in all the cells, and then you decide, and then you rewire them with the following levels of metallization, or this is done later on in some way, and then you have an FPGA-like rewiring process?
So the short answer is that it's done after the manufacturing process, but it's an integral part of the overall manufacturing process, because what we do is, as part of the manufacturing process, along the way we have various tests to discover where the defects are, and based on those defect patterns, we feed that defect map effectively to a low-level software, which we use at the end of the manufacturing process to basically do a configuration, a software configuration to program in all of the, which redundant cores we're using and which redundant links we're using. And so in that sense, it's kind of like an FPGA process. One of the reasons why we think of doing the configuration after the fact is because one, some of these defects, or probably most of these defects, are introduced as part of the fab process itself. But as you can see, the assembly process into the package and the system is also a fairly non-traditional one. And so we want to also be able to capture any defects that may have been introduced in that process. And so it's a final step at the end of the entire system manufacturing that we program in the final defect map and the final redundancy scheme.
And can you give us a sense, maybe this is sensitive, of how many of these cells need to be rewired because they have been defective at one point or another?
Yeah, so I think there's a couple things to note here. One is that we designed the underlying architecture such that there are no redundant cores that are kind of hardwired to be redundant cores. They're actually just the standard cores that we have. It's just a matter of which ones we consider to be redundant or not redundant after the fact as part of this mapping process. And so that actually allows us a great level of flexibility to deal with a wide range of defect densities, right? If there's higher density, we can essentially dedicate more cores to be redundant ones. Now, having said that, like I said, most of the defects we're dealing with here are primarily from the silicon fab, and it's quite typical to have on the order of hundreds of defects per wafer in a advanced, even mature in production process, right? And so that can give you a sense as to the number of cores that we would need to dedicate as redundant cores. In the end, it's actually just a very, very small fraction of the overall cores. We have almost 1 million cores, 850,000 cores, right?
Yes.
So you can kind of get a sense from that as to the order of magnitude of redundancy that's needed.
Wow. Okay. All right. Any questions? I don't see any questions on the chat or the Q&A. Please don't be shy. All right, let me ask another question while we get the audience to prepare questions. So now I presume that you are thinking forward. I was happy with your statement that Moore's law is not dead. In fact, there are several generations coming in the future, and you probably are thinking importing over your designs to future generations. But one of the things that's going to happen at 5, I think you're using 7 nanometer for the latest design, right?
Correct.
One of the things that will happen at 5, certainly at 3, is the move to EUV lithography, which is a completely different animal. With different reticle size and many other constraints. Is your design EUV ready in some way, or would that require really significant re-engineering?
So I would say that to the first order, it is, and it ties in to some of the architecture decisions, one of which I just mentioned in terms of abstracting away most of these physical defects to just core level or fabric level defects. And so we at the higher level architecture level, we're trying to kind of decouple ourselves from the underlying process as much as possible, and allowing ourselves the flexibility to be able to handle various levels of defects. Now, that's from a defect perspective. From a physical design perspective, I would say that it's not true for everything, but for the most part, our design process, we try to adhere to just standard, ASIC process, ASIC design, and so we are not doing anything beyond what, say, a normal processor, ASIC design processor might do. Where things get a little bit trickier is obviously in our cross die domain. But again, there we're using high-level metal layers, which are, essentially, many generations old technology in some sense. And so for the most part, and then this is kind of intentional. For the most part, we've tried to kind of stick within the standard practice as much as possible, so that we can ride the same trends that the ASIC industry has. This is a very kind of pragmatically driven decision, as you might expect.
Very cool. All right, any questions out there? I don't see any, and we have a couple of minutes, so I am taking advantage of your
I've answered all the questions.
You had really a remarkably clear talk, so I can imagine how folks are happy with the presentation. I was very intrigued by the notion that you are using the scribe lines to connect across reticles to have this two-dimensional matrix. And I was interested in how would you solve that problem. So I'm happy that you explained it well. But still, it seems to me that when the process has been designed to fabricate and eventually isolate different chips, there must be a truly dead zone where the manufacturer doesn't put any test devices, but yet you need to right through that dead zone which will really be destroyed by the saw when it cuts through. So is it the case that really you can print all the way to the edge of the reticle with precision?
So that's ultimately the reason why this was done in tight collaboration with TSMC, right? So there was really kind of two main challenges to be solved. One is exactly what you're getting at, which is how do we effectively, print two adjacent masks such that they can get right to the edge and actually connect, right? And that requires some tight collaboration, because this is not typically done.
Right.
But short answer is ultimately yes, we can do that. But it wouldn't have been possible if we didn't have the tight collaboration, because you can't just do this in the standard like with a standard tape out. We had to work very closely with TSMC on the design rules, especially at the edge. Yeah. The second aspect, which was challenging, which we had to co-design with TSMC, is ultimately we essentially packed that entire scribe line area with our wires, and so any test structures that were there essentially get covered, right? Or we have to be very careful to leave enough room for the minimum number of test structures needed for the fab, right? These are not our test structures. And so it required both working with them to carefully place these structures, as well as working into the flow, so to speak, of how when they rely on these structures and after they're no longer accessible, how they can still get the information that they need.
All right, Jean, you have been extremely generous with your time. We really appreciate coming to give this phenomenal talk to our community. Thank you again. Congratulations again. And please come by and visit us sometime.
Absolutely. Thank you so much for having me.
Yeah, thank you. Bye-bye. Have a good day.
Okay.
Good day, everybody. See you soon.